Welcome everybody. I'm disconnected, and I'm going to speak about a case study from a CTF challenge. So a few words about me for those who do not know me. I've got a blog on the internet. I'm also playing CTF competitions, obviously, in the Just Cut the Fish team. By the way, we got 4th place last year worldwide. I'm also a staff security engineer at Trail of Bits, a company where I am performing security audits of software for our customers. And I'm also maintaining some open source projects, mainly Pwn Debug, which you can see on the right side. This is a plugin for GDB that we'll actually use today for debugging Linux kernel. There was this CTF called KalmarCTF 2024 from Kalmar Union CTF team. And by the way, we scored like 6th place there. Could be better, but not bad. And there was this CTF challenge called Msrable. It was a Pwn-able challenge, which means we have to do some kind of binary exploitation here. And let's look at the challenge itself. So in the challenge, we basically get some kind of attachment file, which is a zip file here. And we have a description which says that, I hate having to use sudo every time I want to change the MSRs. Let's just make it global writable. I'm sure that won't cause any security issues. So this is kind of disclosing what we will be doing, but we'll get to it. And there was also a line that I'm missing here, which was showing us like a remote server that we could connect to. And this was the, the organizer server where if we connected to, we got the same environment as the one that we will get from the zip file. And then we had to exploit the Linux kernel. So in the zip file, we actually get 4 files, one of which is a shell script. This shell script, you can see this on the right side. It will launch QEMU. This is quick emulator for emulating Linux kernel. So this will spawn a virtual machine for us with some of those files that are attached here with some kind of configuration. So let's run this run script. So if we run it, it's actually putting up the Linux kernel. There are no logs enabled here. But we are on some Linux machine here, and we are user 1000 or CTF, and there is a flag file that we have to access or read. But this flag file is owned by root. So the thing that we have to do here is we have to escalate our privileges and become root at some point somehow. Obviously, we are not in sudoers. There's not even sudo, and we cannot really gain root privileges normally. So yeah, what do we do? In these files that we received, there is this diff MSR file. This diff MSR file, it contains the following diff, like a git diff. In this git diff, there is this MSR open function from the Linux kernel source code. And the thing that they did is they removed this line here, which is checking for a Linux capability, which is called capsys-raw-io. And this capability is something that a root user normally has, but no other users on the system have it. I mean, you can obtain it in some ways, but normally root user has it. So if we are not root, normally on Linux, we won't be able to access this function. I mean, it will return the the permission error that is being returned. But they removed this check. So this means that we can now open this, call this MSR open. The question is when this is actually called. So it turns out that this is actually called when we are invoking or accessing a device, dev CPU, then the number of the core of the CPU, and then MSR. So we can see this file here, dev CPU 0, because there's just one core here, MSR. There's this file. It's readable and readable by everyone. And if we try to cut it, like basically open and read something from it, something is happening. Obviously, cat is not returning because, cat is not designed to work with this file. But if we, get out of this virtual machine and try to do the same stuff on a normal system, as normal user, not being root, we cannot access this file. This is how it's normally on Linux. Even though I can read and write this file, I cannot because we get this operation not permitted, which actually we can strace it and see the system call for opening this file. It returns this eperm error here, right? So this is what we had here, this eperm. What are those MSRs in the end? Well, we can just use the Linux manual and do man MSR, and we can see a manual page for it. And this is basically an interface for reading or writing model-specific registers on x86 or 64-bit CPUs. And those model-specific registers are like a special registers inside the CPU that allows us to configure certain features of the CPU or maybe read some values from it. And for example, some of those features are like performance monitoring or maybe checking some CPU status or toggling some CPU features. But one interesting thing is that there is this syscall instruction handler there as well, like a special MSR for this particular need. Because, and by the way, syscall is a system call on Linux. So if you are invoking something like open, read or write file or close, or I don't know, forking a process, sending signals to it, it all needs to go through the kernel, and it needs to invoke the syscall instruction on x86. Yeah, so one more thing. There is an Intel manual dedicated for MSRs, and it's more than 500 pages long. So you can imagine there are actually lots and lots of registers, those model-specific registers, and some of those registers are even like specific just for this particular CPU model. But some of them are, available on all of the CPUs. And also under the hood, there are two like CPU instructions to access those. There is this RD MSR and WD MSR for reading and writing, but they are privileged. So only Linux kernel itself, I mean ring 0 or kernel itself can access those or like invoke those instructions. If we try to like invoke them in user space in like normal Linux program, not in the kernel, then we will basically get like some access denied thing. Yeah, so since we now can access those MSRs, because they allowed us, let's maybe read some of them. And here we have some small C program. Here we define some kind of MSRs constants, because there's some interface that we need to fall in, and those MSRs have some numbers. Then we open the MSR file with read-write permissions. Then we read them with some macro that is invoking this read MSR function. This just needs to fit some kind of interface that is designed by kernel. But yeah, if we run it on a demo, here I can run it. So I'm booting up the kernel again. I have demo 3 here that is invoking this code. We can see that we read some values, some of those registers. And some of those values are pretty interesting. I mean, D01 hexadecimal, I have no idea what that is. But for example, this value here is very huge. It basically looks as if that is a kernel pointer. And we can actually confirm it because we can debug this kernel with GDB. And here I have a script that will basically plug into this Linux kernel and attach to it. And now we are debugging Linux kernel with GDB. And so we can take this address and we can, for example, see what is like the memory mapping it is in. And it's in some kind of memory mapping that we can see here. This mapping is executable. So it basically means there is some code there, most likely. We can read this code, obviously, like with the debugger itself. And we can see some instructions here because we disassembled it. And we can also see what is the like symbol for this address. I have this klookup command here that will basically look up the symbol for this address by like reading up lots of memory in the kernel. And we figured out this is the entry syscall64 function. So this basically means that this MSR L star that we can see here, it holds a pointer or an address of the function entry syscall64. And this is actually a function in the kernel that is invoked whenever the syscall instruction is executed. So this means that we actually can leak the kernel addresses. And by that, we can then compute like the base address of the kernel and maybe some other addresses of other instructions there. By the way, I also have in this code, I need to continue this kernel so that it executes. I am also reading, like, for example, MSRs up to the number this number of MSR, and we can see there are some other MSRs here with some potentially kernel pointers as well, but this is like -1 maybe, or some huge number, and so on. Yeah, so we can read MSRs and we can leak addresses. Okay, so what next? Since we have this L star that holds the, that holds the address of where the syscall instruction will jump, can we actually exploit this? Can we use that for ourselves? Because when the syscall instruction is executed, the CPU will jump to this address, and it will switch to the kernel mode, to the privileged mode of the CPU. And so then, well, you can access any memory, for example, in theory. Yeah, so what if we would just point this address to some user space function, like a function that we will define in our program? And here we have an example of that. So we have the main function again. We are basically opening the MSR, and we will change the L star to the address of this infloop function here. It's written with assembly. This jump dollar is basically doing an infinite loop. So if we execute it, and then we should see that the program is getting, or the kernel is getting an infinite loop if it works. So let's see if it works. We have a demo 4 here, and in this demo 4, I can also show you. Well, we have a function called break or breakpoint on this address. This hasn't. The exploit code here hasn't been executed yet. We still didn't call this L star. We have to press enter for it to work. But we have this break function, which we can set a breakpoint there with GDB, with this break command. Then we continue the kernel, and then we press enter here. Now the GDB stopped on this instruction in the user space program, this empty function called breakpoint that we have there. I can actually show you it here. Well, demo4.c. We have this, this breakpoint function here, and it's being executed here. And this is the function that we stopped at. Then we will have this write to the MSR. So if we leave this function, and I will do some magic commands now to jump to the end of the function, then I will jump over some of the instructions that we have here. Here we have a call instruction. This is calling the write MSR function. And afterwards, we are calling the syscall instruction. So if we actually change the L star to the infloop function address, then we will see it will jump to this function. So if we now step into this syscall, we can see that we jumped into some code that is basically doing some weird instruction, but then it's jumping into itself. And this is the infinite loop in this infloop function. So did it work? Well, we didn't execute this code yet. And if we try to execute just one instruction here, boom, we actually jumped back to the kernel code. And what happened here is that we couldn't really access this memory. We couldn't execute this user space memory because there is some protection for it in the kernel. And the kernel jumped into some kind of crashing procedure. We won't see the crash here because we don't have logs in the kernel here. But if I run it with logging, so now we can see all the boot logs. And if I launch the demo 4 again and press enter, we can see here that, well, there is a warning that we write to some unrecognized MSRs, but this is fine. But what is wrong is this traps panic double fault. So, the kernel is basically panicking that, hey, you accessed some memory that you shouldn't have accessed. So this does not work because kernel can't really jump to user space code because of a thing called SMEP, and this is supervisor mode execution prevention. And there's another one called SMAP, supervisor mode access prevention. And those two are mitigations that disallow kernel to execute or access the memory of our programs. Why is it there? Well, because we want to prevent some exploits like this one from having an easy way to execute code in the kernel. And sometimes kernel needs to access user space memory when it wants to copy some data from user space. And in those cases, the kernel is actually disabling the access prevention and then copying the memory and then enabling it back. But well, this is not this case. Okay, so what else can we do? We cannot really jump to user space, but there is. But if you would look up what happens when we actually execute this syscall instruction, so here we are executing it, and here we executed this syscall instruction. The register state of the CPU, particularly the stack pointer, is still pointing to the stack of the user space program. So we can control what we put there, and this will be helpful in a second. And maybe because of that, maybe we can use a technique called return-oriented programming for binary exploitation here. And for those who do not know what is ROP, here's some 101 for it. So when we have a function like this on the left that adds two numbers, and when this function wants to return, so we call the function and then we need to come back to, I don't know, to the main function. What is going on? There is this instruction called ret, which returns, obviously. This ret instruction is basically taking an address from the stack memory and jumps to this address. So if we control the stack memory, we can actually chain jumps like this to a thing that we will call gadgets. And those gadgets will be some very small pieces of assembly code that will end in the ret instruction. We don't really need to know what those assembly instructions are doing, but the basic idea is that if we can control the stack memory, then, and in this case with the foo function, then the program can read to some gadget that we would put there, and then another ret instruction will jump to another gadget, and then the next to a next gadget, and to a next gadget, until we do a jump to some cool function or something, after we set up arguments, for example. So this is the basic idea of the ROP attack. But we need to control the stack memory. And we do control the stack memory, because the stack pointer is pointing to the user space stack. The problem is there is this SMAP mitigation, the access prevention. So even if we try to do that, this ret instruction, when it would try to fetch the data from the stack, it will be prevented by SMAP because, well, this is a user space address, not a kernel space address. So yeah, this won't work here. But coming back to what we had this control over the L star MSR, where we could jump to an arbitrary address, right? In the kernel, for example. So maybe we can do but we can still, so this means that we can still actually do a single jump to some kernel address. We can't really fetch any user space memory. And I can actually show you this. We have demo 5 here that I will run maybe without logging here. And I will have to restart GDB as well. So I launched demo 5. It also has a breakpoint function so that we can set up debugger and break there. So if we break there and continue this program, we are again in this breakpoint function that does nothing. If we go over it, and then here happens the write to the MSR. And what we write there is we fetch the address of entry syscall64, so this address, because we can read it. Then we add some number to it, and that's the address that we replace it with. And so now if we use this syscall instruction, it will jump to this instruction that is in the kernel code. We know that because this address here is huge. This is the kernel address. And we jump to a ret instruction. So that's probably how we would start an attack like return-oriented programming, because now this ret would actually fetch from the stack pointer memory. And if we look up what is there, we can see that on the stack there is this weird value that we would jump to. This address is not mapped anywhere, so this will crash anyway. And obviously we cannot fetch from these memories because of access prevention. But we can see that, for example, this is the argument of the program. This is like an environment variable, so this is the stack of the program. But yeah, this will crash anyway because there is this access prevention. We can't see any logs here because we didn't run with logging. So yeah, so this didn't work, but we can still jump to some other code, right? There are some other instructions in there. But the question is, can we actually maybe bypass SMAP and like find some code that will disable SMAP in the kernel, and then use this return-oriented programming technique? So the thing is that the SMAP prevention is controlled by a bit in CR4 register. There's like a special register, control register 4 in the CPU. And kernel has code to disable it. The problem is, while the kernel has code to disable it, this code is unmapped when we call syscall, because there is a thing called kernel page table isolation, KPTI. And before I tell you what this is, let's go to some basics. So there is this thing called page tables. And when you have two processes on Linux, or on Windows probably the same, those processes will access, when they access memory, like an address X, they are actually using like virtual addresses. So they have some virtual address space from like 0 to 0xFFFF. And the thing is that if you have two processes that wants to access the same address, virtual address X, in the physical memory in RAM, those two addresses, those two memories, can actually point to different pages in the physical memory in RAM. So there is some translation going on from the virtual address to a physical address. And this translation is supported by a thing called page tables. So for a given process, there are some tables in the kernel memory for actually figuring out how to map those virtual addresses to physical addresses. And in the past, when we have a virtual address space of a process on the right side, it turned out that each process had the whole kernel mapped in its memory, in its virtual address space. Whole kernel memory. By the way, whole kernel memory also contains all physical memory, because the space is so huge that it can contain all physical memory. Because while you have, like, I don't know, 4 gigabytes or 64 gigabytes of RAM, this address range from 00 to 0xFFFF is very, very huge. And while the process had all the kernel memory mapped in, it could not access it because of some permission bits in there. But it turned out that there was this meltdown vulnerability, which actually allowed you to access this memory through speculative execution. I won't explain it here. I hope some of you have heard about it. But basically, because there was this meltdown, then the kernel devs added this mitigation called KPTI. So what is KPTI? Well, processes don't really have the whole kernel space mapped anymore. Instead, they just have a bit of kernel mapped in, because when we invoke the syscall instruction, we need to jump to the syscall handler, and this function needs to be mapped in, because otherwise, how that would work? How could it work? And a given process have two set of pages. One is for its own user space, part, and the other part is for the other pages. Page tables are for the kernel part of this process. And in this kernel part, the page tables look like they looked before KPTI. And what happens is that when you execute this entry syscall instruction, this function that is mapped in the process still, there are some instructions that sets the CR3 register, and this CR3 register is actually holding the physical address of page tables. So it's changing the page tables from the user part to the kernel part, and so now kernel can access the whole memory of kernel. But before we execute those instructions, we do not have this mapping in our exploitation part, right? The problem, as I said before, there is the CR4 register that can be disabled by kernel, but gadgets, so those small parts of assembly code that would do that for us, are not really mapped in kernel memory, so we cannot really use them. But the thing is that we can still bypass SMAP and then use ROP. And it turns out that CPUs also have a flags register, because CPUs have a lot of registers. And this flags register, usually it's used for like figuring out whether a subtraction returned 0 or something like this. But there is one flags register which is called alignment check. And I wouldn't say it's widely used. Like user space programs usually probably don't really touch it at all. But the thing is that it says SMAP access check in this description from Wikipedia. And it turns out that maybe we can just disable this bit, and so the SMAP would not work. Well, it's not so simple, because if you look up this description for the syscall instruction in Intel manual, it then says that syscall saves the error flags into some register and then masks this flags register using the IA32 fmask MSR. So basically what is going on is that when we invoke syscall instruction and when we have this bit here, this bit will be checked against the mask in this MSR, the special MSR that is listed here. And if this mask has this bit, then this bit will actually be set. If this mask doesn't have this bit, it won't be set. or something like this. But basically, this means that just disabling the AC bit, the alignment check bit in the flags register won't work. We still need to set the same stuff in this mask MSR. And since we can read and write arbitrary model-specific registers, we can do that. So that's what our exploit will be doing, actually. And I can show you a bit of code for it, because I have the exploit code in here. Wow. Or actually, do I have another example for this? What was demo 5 doing? It was not exempling this. OK, exploit. So this is a bit weird, maybe. But the thing is that, well, what we have to do is we have to figure out the mask there. So we have this MSR syscall mask. And, whoa. Sorry. So in this code here, what we will be doing is that we are reading the syscall mask MSR. We are printing it. And then we are setting the AC bit there. And then we are writing this MSR. And then we also read it back again just to see if it was set. And so this is one part of the exploit. The other part of the exploit is that we actually have to set this AC bit in the flags register. And this is supported by this assembly code. I'm not going to explain it. But this can be done from user space. And then we need to call syscall at some point after we change the L star, right? So the whole idea of the exploit is, and if we do that, then we will have SMAP disabled. So the whole idea of the exploit is that we will read the L star MSR to leak kernel base address so that we can compute other kernel code addresses. Then we will prepare the kernel, we'll prepare the return-oriented programming attack by leveraging some gadgets in the kernel code on the stack, on some kind of fake stack that we will set in the stack pointer register. Then we will disable this access prevention feature by unsetting or setting the AC flags and the mask. So doing the kind of stuff as it's here on the red. And then we will set the L star to jump to the return instruction in the kernel. So this will trigger our ROP, right? Because we disabled SMAP, so we can access user space code and return to the addresses that we will fetch from user space. And then there is one more problem, because eventually what we want to do, we want to change so many gadgets that we will be able to become root. In order to become root, well, what can we do? There are two ways for it. One way for it is that we could actually make some kind of chain that would look over the kernel memory, and it would find the user ID of my process, and it would change it to 0. But using ROP, it may not be so easy. The other way is there is so yeah. By the way, we need to set the CR4. Oh yeah, so it would not be so easy. But the thing is that we also don't have so many gadgets. We don't have so much kernel code mapped in, because what we have mapped in from a kernel is just a bit of memory where the syscall handler is. What we want to achieve is we want this, because then we will have so much code from the kernel and so many gadgets from it, like those small assembly instructions that end with red, that we would be able to reuse. And for doing that, we need to use this CR3 register. That's what I showed you before, that when we enter the syscall, the CR3 register is being changed to some other value, and then the whole kernel is mapped here. And that's what we want to achieve in the end. And for that, there is some kind of gadget that allows us to set CR3 to an arbitrary value in the kernel. But we need to know this value. And what my exploit is doing, it's a bit hacky, because it's just hard coding this value. But I could improve the exploit in theory to compute this value properly. But yeah, my hard coding worked with some brute forcing, so that's what I just did eventually. Yeah, and then, as I said, to become root, one way is to find the user ID in the memory and set it to 0 to become root. The other way to do it is there are those two functions in the kernel called init creds and then commit creds. And if you just call init creds, it will return you the creds object. And then if you then call commit creds, it will reuse this creds object, which will be initialized with all zeros, which means your process will basically become root. I mean, the user ID will become root from your process. Then there is a bit of a problem, because we need to safely return to user space, right? Because we are in the kernel space. I mean, after we became root, you want to read a file from the file system. And to read the file, well, we can do it from the kernel space, but that would not be easy. But it's easier to safely return to user space and then read this file. And this is a bit problematic, because since we set CR free, we now need to set it back to the previous value, because otherwise this won't work, this returning won't work. But it's pretty straightforward, because the thing is that the CR free between the kernel and user part is just changing 1 bit or something. So if we know one of this, then we know the other one. Which means that if we which means that we just have to hard code one value or compute one value of this physical address of page tables that we put in CR3. So let's demo the exploit. I can show the whole code, but it's not so easy to explain all of this, because we are setting this syscall mask, we are mapping some memory so that we can reuse it for ROP or other stuff. We are putting some values here, like this new CR3, this is the hard coding part. And then we are using some gadgets, like, for example, here is a gadget that, like on this address from kernel base, we'll just set the CR3 register based on the RAX register of the CPU, and it performs then some jump somewhere. Yeah, so if we run this exploit, and since I said that we'll have to brute force something, let's maybe run it like many times so that it actually works. Because, in one attempt it may work, in another it may not. Yeah, okay, so the kernel needs to boot up, and since I'm launching like 20 instances of the kernel, it takes a bit of time. As you can see, like 10 seconds. Okay, it booted. So now if we run the exploit, it's printing out some of the values that we had there, and is it working? So now I have to press enter for it to work. So let me hit enter. And in some instances it worked, in some it didn't. You may not see it, but I can zoom up this terminal here, maximize terminal, and here we have we actually read the file, the flag file. Yeah, so as you can see, the exploit has worked. And I can also maybe show you the code for this part, for reading of the file, because I could write it using some kind of normal code, like open a file, read a file, close a file. The problem is, if you remember, we have changed this L star to some other address in the kernel, which means that we basically broke what will happen, changed what will happen when the syscall instructions is invoked. And syscall is used for opening a file, writing to it, and so on. So how the hell do we invoke a syscall now? Well, it turns out that there is another way for invoking syscalls, or actually invoking 32-bit versions of syscalls, which is this other instruction called int, like interrupt 80 in hexadecimal. So here we have assembly code that will basically perform opening of a file, reading of it, and writing it to the console using, 32-bit assembly. And, since this instruction handler for this kind of syscall, 32-bit syscalls, is stored in a different model-specific register, we can use it. And so that's what I did, and it works, as you have seen. Yeah, so here are a couple of syscalls that is basically doing some open of a file, getting its size, and then sending it to the console. Yeah, so here is the same exploit on the slide. If it didn't work on the demo, but it worked. Yeah, so to sum up, we can actually use the MSRs if we have like arbitrary read-write to get a privilege escalation. So now the question is, how does this relate to any real-world stuff? Well, it turns out that some drivers that you install or use, like, I don't know, for some stuff that you may want to use from your CPU, may actually access these MSRs, because root user can access this device. And if this driver would have a bug that you would be able to exploit from user space, then you could use this technique that I showed you to gain privilege escalation on Linux. As you have seen, there are a couple of mitigations. There is SMAP, SMEP, KPTI, which is kind of pain in the ass, but it works. You can set where you will jump with syscall, which means you can, point to any code in the kernel, or well, this small piece of kernel code, and you can jump there. We can also bypass SMAP by using this alignment check and this other syscall mask MSR. And then we need to trigger, or we can trigger the return-oriented programming attack. And, well, setting proper kernel page tables helps here, as you have seen. So that's it. Thank you very much. And also 2 more things. If you can, please rate the talk in the inventory app. And also, we are actually organizing a CTF, which is called Just CTF. There will be 2 editions. Well, there will be finals that will be on Hackia event in September in Taron Arena. This will be open, so you don't really need to qualify for it or anything. But there will also be a teaser CTF in 2 or 3 weeks, in 15th of June. There will be online, open to any teams from the whole world. And the top teams will get some reimbursements for getting to the finals. And by the way, on the finals, we'll also have a special ranking for academic teams. So yeah, feel invited. And that's basically it. Thank you very much.